Okay, so chapter 3, we're going to be talking about derivatives. I assume that they're showing that because derivatives are a rate of change, so they have a lot to do with motion, and so a fast car, you know. No, I do not. What kind of car is it? Oh, it's a. Oh, see what it says right there? From 0 to 200 in 14.51 seconds. It's a fast one. I know. Okay. So today we're going to talk about something called the derivative. Okay. So a derivative is going to give us information about the rate of change of something. Okay. So we're going to talk about how it relates to tangents and tangents at a point on a curve. We're going to talk about calculating the slope of a tangent correctly. Up to this point, we have guesstimated where those tangents slopes are, and now this is going to help us get an exact, precise answer. So remember, when we looked at our graph, if we were at a tangent line or at a point where we were going uphill, our tangent has a positive slope. If we were going downhill, our tangent line had a negative slope. And if we were at a peak or a valley, our tangent line was 0. So that's important to know. The slopes of the tangents give us lots of information about how our graph changes and how it increases, decreases, or may have a absolute or local min or max. So we're going to have to look at those things, and that's where this is going to take us, okay? There's two different types of notation. That's Newton on the left and Leibniz on the right. They came up with calculus notation about the same time, and there's arguments as to who discovered it. Most people talk about Newton and Newton's notation a little more than the Leibniz notation. We're going to use in this class a little bit of both people's notation, so because some are a little more useful than others. So yes. Yep, same guy. That guy on the left is the one that gravitation, and he supposedly got hit on the head with an apple. I don't know. So let's recall that the slope of a secant is just y2 minus y1 over x2 minus x1. But that is a function notation way of saying that. A slope of a secant is just the slope between 2 points. Okay, and we can write it a mixture of ways. You'll see it sometimes written like this. You'll see it sometimes written at, we have moved some h away from a, so you'll get something sometimes that looks like that. Most of the time, for our purposes, just use your normal slope equation when dealing with the slope of a secant. But we will be using this is called the difference quotient. We have moved a difference of h away from our original point. We will be using that difference quotient here and there, depending upon what we're trying to accomplish. But just remember, the slope of a secant is the slope between 2 points. A tangent, we only have one point of concern that we are looking at. This is the difference quotient. That one there, that version there is called the difference quotient. And basically, it's just taking some point on your curve at A, adding some amount h, and then it always reduces down really, really nicely. So we will talk about the difference quotient depending on what we're doing. Most of the time, when you're just doing slope, that one's going to be helpful. There's going to be some things we're going to do where the difference quotient will be a little more useful. So that's the difference in a picture. In this first picture, our first point is A, our second point is X. So you can see the two distinct points. Here we started at A, we moved a difference of H. In the second picture, we've gone a difference of H, and then it reduces down a little differently. So both can be useful. Both are the same exact thing. One is, the notation's a little different than the other. One's not any better than the other. Mathematically speaking, sometimes this one's a little more helpful because we can reduce it down a little better than this one. This one is useful a lot for polynomials. This one's useful for a little more complicated kind of stuff, square roots, fractional functions like our rational functions. So, but they mean the exact same thing. Here we just have two distinct points. Here we have scooched over an amount of H, and that's why we have jumped over a difference of H. So that's the difference. But pretty much same thing. Now here's the difference. Let's look at the difference in what we saw on the last page. For a secant, we had two distinct points. Here, we are getting super, super close to A. So as we get super, super close to A, it becomes a tangent and no longer a secant. Here, our difference between A and A plus H is 0. So that is the difference. You have those limiting quantities in front. So a slope of a tangent, we're going to have to use our limit rules. So the rules we learned in chapter 2 don't go away. You still have to, you may have here, if you plug in 0, we may have something where we get a 0 over 0 sort of thing happen. So you have to manipulate the algebra. Here, you still might get 0 over 0 at A, so you might have to manipulate the algebra. So the rules aren't going to go away. These are still limit rules. So you still have to do, those same limit rules that we have learned from before. So that's why, we'll keep reviewing those limit rules until they hopefully get stuck in your brain. Eventually, we will actually even know more of a shortcut than even this. Big 3-3, we do that, huh? Oh, this? That's just what they've named in the book. They have called this formula 3-3. So in the homework, if any formula is mentioned, use a particular one. They're just pointing you back to the right formula. But I'll kind of direct you to as to what formula. Yeah, that's just the name of the number they gave that formula. So that's the 3-3 formula and the 3-4 for the slope of the tangent. Okay. We are going to need to find the equation of our tangent lines. To do that, we're going to find the derivative of the equation, which will then give us the slope of the tangent, and then we're going to plug that original point and slope into your y minus y1 equals m times the quantity of x minus x1. I have put this little t here just to remind you that that's the slope of the tangent line. And think about how we do any sort of equation of a line. We need a point, we need a slope. So these two steps are just giving us that slope. And then we plug that point and that slope into the y minus y1 equals m times the quantity of x minus x1. We're going to do the tangent, that derivative thing that we'll talk about here in a second. We're going to do that kind of the long way is with our difference quotient. And then we will get some shortcut methods eventually here in this chapter. So as we go through the chapter, it's going to start out a little more difficult, unlike some chapters, and it's going to get easier before it gets harder. Okay, so let's look at our first example. It says use equation 3.4, so that's what we were talking about, to find the slope of the tangent line to the graph of f of x equals x squared at x equals 3. So I've cut and pasted a little picture of the formula we're going to use for the slope of the tangent. Okay, so this is what I suggest doing when we're using the difference quotient. There are two main pieces we have to find: f of a plus h and f of a. So first, above here, let's plug in a plus h, and let's plug in a. Let's plug in those things. Let's find those particular items. If we plug in a plus h into our function, so here's our function, and we're just using what we know about plugging things into functions. That's a plus h squared. And remember, that's a plus h times a plus h. So you do have to FOIL that. If you don't multiply that out right, you're going to get something funky. That's going to be a squared plus 2ah plus h squared. And then f of a is just plug a into the function. That's an easy one. That's just a squared. And now that we have what those two items are, let's plug it in. So the slope of our tangent is going to be the limit as h approaches 0. And I'm going to write in f of a plus h. So f of a plus h is just a squared plus 2ah plus h squared minus f of a, which is a squared, all over h. Now, you want to reduce that down as much as possible, because at this time, if you plugged h into your formula, you would get something super funky, okay? You would get, I think, 0 over 0, so that's not super helpful. So what we want to do is let's go ahead and simplify that as much as we can. So we get a squared plus 2ah plus h squared minus a squared all over h. The a squares can cancel out. So we're going to get the limit as h approaches 0 of 2ah plus h squared over h. Now, at this time, if you tried to plug in 0, you would find that you would get 0 over 0. So that means that there's still something we can do for the algebra. At this point, what's great about the difference quotient is everything in the top that's left should be divisible by h. Now, do we have an h in both of the terms that are in the thing? Yeah. So that means that we can divide both of these pieces by h. So let's do that. And we get 2a plus h. Everybody with me so far? And now, can we plug in h0 without any problems? Sure. You get 2a plus 0, right? Which is 2a. So what we just have found, that the slope of the tangent is always 2 times the a value that we're trying to find the point at. Well, what's great is they told us right here, at x equals 3, means that our a value is 3. So now we just get to find our a value, find our slope by using that a value. And so our slope of our tangent is just 2 times 3, or 6. So now we know at the point when x equals 3, so the point 39 on our graph, the tangent line has a slope of 6. Yes?
When you divided 2ah plus h squared divided by h,
Uh-huh.
wouldn't it be 2a plus h?
2a plus h, but we're going to plug in 0, and then that means the h goes away, and so it's just 2a. Yeah. So you are right. That's what we get. We get 2a plus h, but when we plug in, do direct substitution and plug in 0, we get just a 2a. Did everyone see how we got the slope of our tangent? Now, there's more than one formula we could have used. We could have used that 3-3 formula. 3-4 formula is usually a pretty nice one to that difference quotient. Okay, so now let's go back up to here. Do you see in example 3-1, it says find the equation of the tangent line at f of x equals x squared at 3. So remember, we already found the slope of the tangent was 6. Same exact problem. We already found that the slope was 6. So all you need to find a tangent line is, remember, you need the point, you need the slope, and then you get to use y minus y1 equals m times x minus x1. So we don't have the point completely, right? If the x is 3, plug it into your equation. 3 squared is 9. So now we have a point and we have a slope. We know how to find an equation of a line at that point with that slope very easily. You're just going to do y minus y1 equals m times x minus x1. Now, for me, I mean, that's the equation of the line. I mean, but depending on what you're trying to do with that equation, sometimes it's helpful to make it a little nicer. If we distribute the slope and add 9 to both sides, we get that the equation of the tangent line is y equals 6x minus 9. Very straightforward, very easy. The hardest part is finding the slope of the tangent, which eventually you'll have some formulas for and you'll know how to do it even quicker, okay? But it required that we are careful with our algebra, plug in 0 eventually to the simplified version. There is the equation for the slope of a tangent, and then you just plug in that a value. So does everybody see how I got those two things? Everybody see how I got those things? Okay. You're welcome. Okay. Now here, they chose to use the other formula, 3-3, to find the equation of the tangent line. So remember, the first thing we have to do is find what's our slope. So they're going to use formula 3-3. So our a is 2. Just say that. Thank you so much. So let's think about what they want us to plug in. They want us to plug in f of x and f of a. So you can plug in just a plain old generic a, which I like to do because then we have an equation that will just always work for that particular function. Or you can actually plug in 2. So if you want, you can actually plug in 2 ahead of time. Yes. I think so. Yeah, I think so. So let's go and let's see here. Okay. So first, let's just find out what is f of x minus f of a over x minus a. Okay. So f of x is 1 over x. F of a, you can leave it 1 over a, or if you want, you can plug in the number. Doesn't matter. If too many variables mess with your brain, you can do that ahead of time. And if we take the limit of that, remember that's our slope of our tangent, as x approaches 2. Now, at this time, if you tried to plug in 2, guess what we get? 0 over 0. It messes up the algebra. But 0 over 0 means that we can fix that problem. So if we fix that problem, how can we fix that problem? Well, here's the trick. For polynomials, the trick is going to be to factor it. To fix a square root problem, you use the conjugate. To fix a fraction, let's multiply through by the denominators of the things on top. The fractions that are inside the fraction, if you multiply through by the common denominator, you are going to fix the problem. So I'm just going to multiply the top by 2x. And whatever I do to the top, I also will have to do to the bottom. If I multiply the top, now watch what happens. If you've chosen the correct denominator, something nice should happen. The 2x multiplies on the top. 2x times 1 is 2x, but I can divide by the x. And so I'm left with a 2. If I multiply 2x times this top, I get 2x divided by 2, and I'm left with an x. The bottom, don't multiply it, just leave it alone. Here's why. At this point, whatever factor was down in the denominator causing an issue will probably cancel out. So you'll notice that we have an x minus 2 and a 2 minus x. Those technically are opposites. Check. The 2 has an opposite sign, right? The x has an opposite sign. So you are allowed to cross out a turned subtraction as long as you leave a negative 1 behind. Okay, so you're allowed to cross out a turned subtraction. They are the same number. It's like a negative 7's on top and a positive 7's on the bottom. You can cross it out as long as you leave a negative 1 behind. So we are allowed to cross those out as long as we leave a negative 1 behind. And so we get the limit as x approaches 2 of negative 1 over 2x. Now at this point, if we did the algebra correctly, we should be able to plug in 2 without any issue. And if you plug in 2, you get, well, we don't even have to write that anymore, because we're allowed to plug in 2, just plug it in, and we get negative 1/4. So the slope of our tangent is negative 1/4. So we have the point. The point was 2 1/2. The slope of our tangent is negative 1/4. So now we get to use y minus y1 equals m times x minus x1. So we have the point, we have the slope, plug it in, we got the equation of our tangent line. So we get y minus 1/2 equals negative 1/4 times x minus 2. Our point was 1/2, 2. Our slope is negative 1/4. Plop it in. We don't have to do too much. We could make it a little prettier. If we distribute the negative 1/4, we get negative 1/4 x plus 1/2. If you add 1/2 to both sides, you get y equals negative 1/4 x plus 1. Now, here's how you check your work, okay? If you go to Desmos, and if you plug in the original function, f of x equals 1 over x, and then you type in the equation that we just found, let me show you. So if we type in y equals 1 over x, and then you type in your equation of your tangent line, you should see that at the point 2 1/2, that it skims across it, it hits just at that point, it's all lovely and wonderful and good. So you can check your algebra graphically. If you type both the original equation and your slope of your tangent, it should hit that point perfectly, and it should skim across it. So you can check your work through Desmos. So use it as a tool to check that you're doing it right. Any questions about that one? Well, let's do one more and then we'll stop and you can start looking at. Now, if they want you to use the same equation again and again, and they say to find the slopes of the tangent lines to the graph of the function f of x equals square root of x at 3 different points, we are just going to use the generic a, okay? So let's do our difference quotient. We are going to do that the slope of our tangent is the limit as h approaches 0 of f of a plus h minus f of a over h. So we're not going to pick an a right now because we're going to have to do it with a being 1 and then a being 4 and then a being 9. We're going to have to do it 3 times. So why not just leave a kind of a generic a so we get a formula for the slope of our tangent, so then we can go backwards and plug it in. Okay, so let's think about what f of a plus h is. F of a plus h is just the square root of a plus h. Do I know what else that is? No, I don't know. F of a is just the square root of a. Now let's put those where those belong. Okay, we're just going to put those where those belong. So it's the limit as h approaches 0 of the square root of a plus h minus the square root of a all over h. Now we know that if we're trying to find a limit as we approach 0, the first thing we try is to plug in 0. If you plug in 0, magically you're going to get 0 over 0. That happens many, many times with these. But we know we can fix the algebra. Now we're going to fix the algebra with the conjugate. So we're going to multiply the top of this fraction times square root of a plus h plus the square root of a. And we're going to do that same exact multiplication on the bottom. Now on the bottom, we're not going to do that multiplication. We're going to leave it kind of this generic, leave it alone. But the top is where we need to fix that with a conjugate, okay? Now, if we physically multiply the tops, that's the difference of squares. So when we square root, the square root pops off. So we end up getting a plus h minus a. And you can physically do the FOIL if you want, but that's what you always get. First term squared minus last term squared. It's the difference of squares. On the bottom, leave it alone. Just leave the h there, leave the square root in parentheses. Now on top, there should be something happens so that you end up getting an h. And we do. The positive a and the negative a cancel each other out, leaving me with an h. And then every single time, the h that's in the bottom should cancel out. So you should end up with an h on the top and h on the bottom. Now, sometimes it's a 2h on top or a negative h on top. So when you cancel it out or divide it out, just be careful with that. H divided by h is 1. So we get the limit as h approaches 0 of 1 over the square root of a plus h plus the square root of a. Now, plugging in 0 works. We don't get 0 over 0 anymore. If we plug in 0 for the h, only the h, we get 1 over the square root of a plus the square root of a, or 1 over 2 square root of a. Now we have a formula for the slope of our tangent. The slope of our tangent is just 1 over 2a, no matter what the a is. So now we're ready to find the slope of our tangent. So I just plugged in 0. So now I'm allowed to plug in 0 for the h alone. That's 0, because we can use direct substitution because it's a number that works in that domain. So just plug in 0 and you get 1 over the square root of a plus the square root of a. Okay. So now go backwards. The first point we were supposed to pick was 1, 1. So the slope of that tangent is just 1 over 2 times the square root of 1, or 1/2. And you can even find the equation of that tangent line at the point 1, 1. It's y minus 1 equals 1/2 times the quantity of x minus 1. We could do it again for the point 4, 2. It's 1 over 2 times the square root of 4, which is 1/4. You could find the equation of that tangent line if you wanted to. Y minus 2 equals 1/4 times the quantity of x minus 4. And then we could do it again for 9, 3. The slope of the tangent is just 1 over 2 times the square root of 9, or 1/6. Same thing, if you wanted to find the equation of the tangent line, y minus 3 equals 1/6 times the quantity of x minus 9. So, that generic formula, leaving the a there, is very powerful, because then you get an equation for the slope of the tangent that can be used again and again and again for that particular equation. So it's very helpful at times to just leave it there and leave the a there. Yes. I like using the difference quotient one. The h approaches 0. It is one, to me. I don't use the other formula very often unless they specify it, or if it's a polynomial, sometimes it will work pretty good because you can factor it. But if it's anything else, square root, fractions, I must always use this version. Yeah. You can use really either, but this one is, I think, the most useful. The h will always cancel if you did the algebra right. The h will always cancel if you did the algebra right. Okay. Now we're going to stop here. We'll continue this tomorrow. But you have enough information that you can start the homework that you see here. All this stuff is on next 9 weeks. So if you did not turn in anything from last week, make sure you get it to me tonight so that I can put in that grade if you're missing anything. No. Every teacher will probably pick a certain cutoff. I just decided I want last week's work in, and we're going to quit the grade from last week's work. So late stuff due tonight.